Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting through the quiet darkness of space to explore something that has captured human imagination since the first curious eyes looked upward. We're going to talk about planets. Those wandering lights that move against the backdrop of fixed stars. Those worlds that orbit in silence, each one carrying its own story written in rock, ice, gas, and perhaps even life. If you find peace in these gentle journeys through science, I invite you to like and subscribe. It helps others discover this quiet corner where wonder meets rest, one sleepy mind at a time. But for now, all you need to do is settle in. Let your breathing slow. Allow your thoughts to drift like dust in a sunbeam. And let's begin our voyage through the planetary realm. The word planet comes from the ancient Greek planets, meaning wanderer. Our ancestors watched the night sky with patient eyes and noticed that while most stars remained fixed in their celestial positions, a handful of bright objects moved. They wandered across the constellations, tracing invisible paths that ancient astronomers tried to map and understand. These wanderers were special, mysterious, divine even. They were named after gods and woven into stories that tried to explain their motions and meanings. Today, we know that planets are something both more wonderful and more comprehensible than those early observers could have imagined. They are worlds, entire spheres of matter held together by their own gravity, orbiting stars in the vast cosmic ocean. But what exactly makes a planet a planet? For most of history, the definition was loose and intuitive. If something moved against the stars and appeared to wander, it was a planet. Under that ancient definition, the sun and moon were planets, while Earth was not. As our understanding deepened, the definition had to evolve. In our modern understanding, shaped by observations and refined by scientific debate, a planet is a celestial body that orbits a star, is massive enough for its own gravity to pull it into a roughly spherical shape, and has cleared its orbital neighborhood of other debris. This last criterion is what distinguishes planets from smaller bodies like asteroids, or from the dwarf planets that share their orbital space with countless similar objects. These requirements might sound technical, but they describe something profound. A planet must be massive enough that gravity has won over all other forces, crushing the body into a sphere. It must dominate its region of space, either by incorporating nearby material or by flinging it away through gravitational interactions. This is why Pluto, beloved as it may be, was reclassified as a dwarf planet in 2006. Not because it lost any of its inherent wonder, but because it shares its orbital neighborhood with thousands of similar objects in the Kuiper Belt, unable to gravitationally dominate its region the way true planets do. The existence of planets is not random. These worlds emerge from the same processes that create stars, born in clouds of gas and dust that collapse under their own weight. Every star system we observe tells a story of formation, of matter organizing itself into patterns that follow fundamental physical laws. Some of those patterns become planets, spheres of rock or gas or ice that circle their stars in paths shaped by gravity's invisible hand. When we look at planets, we are looking at what matter does when it has billions of years to follow the rules of physics. We are seeing the universe organizing itself, creating complexity from chaos, structure from randomness. In this journey tonight, we will visit the planets of our own solar system, each one a distinct world with its own personality and history. We will venture beyond our cosmic neighborhood to explore the thousands of exoplanets discovered around distant stars, strange worlds that challenge our understanding and expand our sense of what is possible. We will trace the story of how planets form, how they evolve, and what secrets they still hold. The universe has scattered planets throughout the cosmos like seeds, and each one offers a different window into the processes that shaped the universe itself. The birth of planets. Formation from cosmic dust. Planets do not appear from nothing. Their story begins in the cold darkness between stars, in vast clouds of gas and dust called molecular clouds. These clouds can span light years, filled with hydrogen and helium left over from the Big Bang, mixed with heavier elements forged in the hearts of ancient stars that lived and died long before our sun was born. Within these clouds, something extraordinary happens. A region becomes slightly denser than its surroundings, perhaps disturbed by the shock wave from a nearby supernova or simply by random fluctuations in the cloud's structure. Once a region is denser, it has slightly more gravity, and it begins to pull in more material from around it. This process feeds on itself. More mass means more gravity, which attracts more mass, and the cloud begins to collapse. As the cloud collapses, it spins. All clouds have some rotation, inherited from the motion of the galaxy and the turbulence within the cloud itself. As the cloud shrinks, conservation of angular momentum makes it spin faster, the same way an ice skater spins faster when pulling in their arms. The collapsing cloud flattens into a disk, with most of the mass falling toward the center where gravity is strongest. This central concentration of matter grows hotter and denser as gravitational energy converts into heat. Eventually, if enough mass accumulates and the temperature climbs high enough, nuclear fusion ignites in the core and a star is born. But not all the material falls into the star. The rotating disk around the young star, called a protoplanetary disk, contains the raw materials for planet formation. This disk might contain only a small fraction of the total mass in the system, perhaps 1 or 2%. But that is still an enormous amount of matter spread across billions of kilometers. Within this disk, the story of planets begins. The process that transforms dust into worlds is called accretion, and it happens through a series of elegant steps that play out over millions of years. At first, the disk is filled with tiny particles, grains of dust smaller than the width of a human hair. These grains are made of various materials depending on their distance from the star. Close to the star where temperatures are high, only materials with high melting points can remain solid. Metals like iron and rocky minerals like silicates. Further out where it is cooler, ices of water, methane, and ammonia can condense. This temperature gradient creates a natural division in the types of materials available at different distances from the star, a division that will ultimately determine what kinds of planets form in each region. The dust grains drift through the disk, occasionally bumping into each other. When they collide gently, electrostatic forces can make them stick together, like dust clinging to a surface. These tiny aggregations grow slowly at first, building up grain by grain. As they reach the size of pebbles and then rocks, gravity begins to play a role. Objects with more mass have more gravity and can attract other objects. The process accelerates. Pebbles grow into boulders, boulders into kilometer-sized planetesimals, and planetesimals into moon-sized protoplanets. Recent research has revealed that planet formation may occur in two distinct phases, particularly in systems like our own solar system. In the inner regions, close to the star, where temperatures are high, planetesimals formed early, while the protoplanetary disk was still rich in material. These inner planetesimals experienced intense heating from the decay of radioactive elements trapped within them. This internal heat was strong enough to melt their interiors, causing denser materials like iron to sink to the center and form cores, while lighter rocky materials floated to form mantles. This process, called differentiation, also drove volatile materials like water out of these bodies, leaving them dry. This explains why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are rocky and relatively depleted in water compared to the outer solar system. The outer regions of the protoplanetary disk tell a different story. Beyond a certain distance from the star, called the snow line or frost line, temperatures were low enough for water ice to remain solid. This dramatically increased the amount of solid material available for planet formation because ice is abundant in space. Planetesimals in this region formed later and grew larger because there was simply more material to work with. Because they formed later, the radioactive heating that had melted the inner planetesimals had already declined significantly. These outer planetesimals remained colder, retained their volatile materials, and formed different kinds of cores. Once these cores grew massive enough, about 10 times the mass of Earth, their gravity became strong enough to capture huge amounts of hydrogen and helium gas from the surrounding disk. This is how the gas giant planets formed, growing into massive worlds that retained compositions similar to the original cloud from which the entire system formed. The process of planetary formation is surprisingly fast on cosmic timescales. The initial collapse of the molecular cloud and the formation of the protoplanetary disk happens in a few 100,000 years. The growth of planetesimals and protoplanets takes a few million years. The final stages of giant planet formation, capturing vast atmospheres of hydrogen and helium, must happen before the star's stellar wind blows away the remaining gas in the disk, which occurs within the first 10 million years of the star's life. By astronomical standards, this is a blink of an eye. Our entire planetary system, with all its complexity and diversity, assembled itself in less time than it takes for a single orbit of the galaxy. But the story does not end with the formation of protoplanets. The early solar system was a violent place, filled with countless planetesimals and larger protoplanets whose orbits were not yet stable. These objects collided with each other in impacts that could shatter smaller bodies or merge them into larger ones. The final assembly of the terrestrial planets involved countless collisions. Earth itself is thought to have been struck by a Mars-sized protoplanet in a collision so massive that it vaporized rock, created a disk of debris around the young Earth, and formed the Moon from that debris. These late-stage collisions continued for hundreds of millions of years in what is called the Late Heavy Bombardment, a period when asteroids and comets rained down on the inner planets, pockmarking their surfaces with craters. For the outer planets, gravitational interactions shaped their final configurations. As Jupiter and Saturn grew, their immense gravity stirred up the orbits of smaller bodies throughout the solar system. Planetesimals were scattered inward and outward, some of them impacting the inner planets and delivering waters and organic compounds that would later become important for life. The gravitational dance between the giant planets may have caused them to migrate inward or outward over time, reshaping the entire architecture of the solar system. Some models suggest that this migration triggered the late heavy bombardment by scattering objects from the outer solar system into planet-crossing orbits. The formation of planets from dust is a testament to the power of gravity and the inevitability of structure emerging from seemingly chaotic matter. Given a disk of gas and dust around a star, planets will form. The details will vary. Some systems will have giant planets close to their stars. Others will have only small rocky worlds, and still others might have configurations we have not yet imagined. But the basic process appears to be universal. Wherever we find stars, we find planets. The galaxy is teeming with worlds, each one born from the gradual accumulation of dust into something magnificent. Our solar system's architecture. Our solar system is a nested hierarchy of structure, organized by gravity into a series of regions that reflect the conditions present when it formed 4.6 billion years ago. At its heart burns the Sun, an ordinary yellow star that contains 99.86% of all the mass in the solar system. Everything else, all the planets, moons, asteroids, comets, and dust, makes up less than 0.2% of the total mass. Yet it is in that small fraction that we find all the diversity and complexity that makes our cosmic neighborhood so fascinating. The Sun dominates not just by mass, but by influence. Its gravity holds everything in orbit, keeping planets from flying off into interstellar space. Its light warms the inner worlds and drives weather systems and climate. Its magnetic field extends outward in a bubble called the heliosphere, protecting the inner solar system from some of the cosmic rays and interstellar radiation that permeate the galaxy. The solar wind, a stream of charged particles constantly flowing outward from the Sun, shapes the magnetospheres of planets and strips away the atmospheres of worlds that lack strong magnetic fields. The Sun is not just the center of the solar system. It is the organizing principle that defines how everything else behaves. Moving outward from the Sun, the solar system divides into distinct regions. First come the inner or terrestrial planets: Mercury, Venus, Earth, and Mars. These are small, dense worlds made primarily of rock and metal. They formed in the hot inner regions of the protoplanetary disk where only high-temperature materials could condense. They all have solid surfaces that bear the scars of ancient bombardment. They all lack the massive atmospheres of hydrogen and helium that characterize the giant planets, though Earth and Venus have substantial secondary atmospheres composed of heavier gases. These four worlds represent variations on a theme: each one shaped by its distance from the Sun, its size, and the accidents of its formation history. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky objects ranging from dust particles to bodies hundreds of kilometers across. This is not a failed planet, though it is often described that way. Rather, it is material that never accreted into a planet because Jupiter's immense gravity prevented it. The asteroids are remnants from the early solar system, fragments of rock and metal that have survived largely unchanged for billions of years. The largest object in the asteroid belt is Ceres, massive, enough to pull itself into a spherical shape, classifying it as a dwarf planet. Studying asteroids gives us a window into the conditions and processes of the early solar system because these objects have not been subjected to the melting and differentiation that have erased the early histories of larger worlds. Beyond the asteroid belt lie the giant planets: Jupiter, Saturn, Uranus, and Neptune. Jupiter and Saturn are gas giants, massive worlds composed primarily of hydrogen and helium, with relatively small rocky cores. They are miniature versions of failed stars, containing the same elements but not quite massive enough to ignite fusion in their cores. Uranus and Neptune are ice giants, somewhat smaller than Jupiter and Saturn, and with compositions dominated by heavier elements like water, methane, and ammonia, in addition to hydrogen and helium. These outer worlds formed where temperatures were low enough for ices to condense, giving them access to more building material and allowing them to grow large. All 4 giant planets have ring systems, though only Saturn's rings are prominent enough to be seen easily from Earth. All 4 have extensive families of moons, some of which are large enough to be planets in their own right if they orbited the Sun instead of their parent worlds. Beyond Neptune, the solar system stretches into the realm of ice and darkness. The Kuiper Belt is a ring of icy bodies that extends from about 30 to 55 astronomical units from the Sun. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers, so the Kuiper Belt is unimaginably far away in human terms. The Kuiper Belt is home to the thousands of known objects and likely millions more, including dwarf planets like Pluto, Haumea, and Makemake. These bodies are made primarily of rock and various ices: water ice, methane ice, nitrogen ice, frozen solid in the cold darkness. They are relics from the formation of the solar system, material that never accumulated into a planet. Even further out, at the very edge of the Sun's gravitational influence, lies the Oort cloud, a hypothetical spherical shell of icy objects that may extend halfway to the nearest star. We have never directly observed the Oort cloud, but its existence is inferred from the orbits of long-period comets that occasionally fall inward toward the Sun. These comets have such elongated orbits that they must come from a vast reservoir of objects surrounding the solar system at enormous distances. The Oort cloud may contain trillions of icy bodies, each one a tiny, frozen world that has remained virtually unchanged since the solar system formed. Objects in the Oort cloud take millions of years to complete a single orbit, moving so slowly and so far from the Sun that their connection to our star is tenuous at best. The architecture of the solar system is not random. it reflects the temperature gradient that existed in the protoplanetary disk, with rocky materials dominating close to the Sun and icy materials abundant in the outer reaches. It reflects the timing of planet formation, with inner planets assembling quickly from limited material and outer planets growing large on abundant ices before capturing massive atmospheres. It reflects the dynamical evolution that followed formation, with gravitational interactions between planets shaping their final orbits and scattering smaller bodies to the distant reaches of the system. Every detail of our solar system's structure tells a story about how it came to be, a story written in the positions, compositions, and motions of countless objects bound together by gravity. Planetary atmospheres and weather. Invisible envelopes. Atmospheres are among the most dynamic and complex aspects of planetary science. Invisible envelopes of gas that can protect a world or transform it into a hellscape. Understanding planetary atmospheres requires grappling with fluid dynamics, chemistry, thermodynamics, and radiation physics all at once. Each atmosphere tells a unique story about its planet's history, its current state, and its future evolution. An atmosphere is held to a planet by gravity, a delicate balance between the planet's ability to retain gas and the tendency of atmospheric particles to escape into space. Whether a planet can maintain an atmosphere depends on several factors. Larger planets with stronger gravity can hold on to lighter gases like hydrogen and helium, which is why the giant planets have such massive atmospheres. Smaller planets like Mars struggle to retain even heavier gases, and tiny bodies like the Moon and Mercury cannot maintain atmospheres at all because their escape velocity is too low. The temperature of the atmosphere also matters. Hot gases move faster, and if the thermal velocity of gas molecules exceeds the escape velocity, the gas will gradually leak away into space. This is why atmospheres erode more quickly on planets close to their stars or on smaller bodies where gravity is weak. The composition of an atmosphere depends on where and when the planet formed and what has happened to it since. Primordial atmospheres, captured directly from the protoplanetary disk, consist mainly of hydrogen and helium, because those are the most abundant elements in the universe. Jupiter and Saturn retain their primordial atmospheres because their massive gravity can hold onto even the lightest gases. Secondary atmospheres form later through volcanic outgassing, which releases gases trapped in a planet's interior, or through impacts of comets and asteroids that deliver volatile materials. Earth, Venus, and Mars have secondary atmospheres formed primarily through outgassing, though Earth's atmosphere has been profoundly modified by life, which produced the oxygen we breathe. Temperature structure in an atmosphere creates layers with distinct characteristics. Near the surface, solar heating warms the ground, which in turn warms the air above it. This creates a region where temperature decreases with altitude, called the troposphere, where weather occurs. Above this, absorption of solar radiation by certain gases can create a temperature inversion where temperature increases with altitude. On Earth, the stratosphere warms with altitude because ozone absorbs ultraviolet light. On other planets, different chemistry creates different temperature structures. Understanding these layers is essential for predicting how atmospheres circulate and what kind of weather patterns might develop. weather and climate are the result of energy transport within an atmosphere. The Sun heats planets unevenly, more strongly at the equator than at the poles, and more on the day side than the night side. Atmospheres respond by circulating, carrying heat from warm regions to cool regions through winds. On Earth, this creates familiar patterns like jet streams, trade winds, and the circulation cells that distribute heat from the equator toward the poles. On other planets, the patterns differ. Venus has a peculiar atmospheric superrotation where winds at cloud level circle the planet in just 4 days, even though the planet itself takes 243 days to rotate. The mechanism driving this superrotation is still being studied. Jupiter and Saturn show banded structures where winds blow in alternating directions at different latitudes, creating the visible stripes. Understanding planetary weather requires detailed computer models that can simulate atmospheric dynamics, and even with such models, many mysteries remain. Clouds form when gases condense into liquid droplets or solid particles. On Earth, clouds are made of water, but other planets have clouds of very different composition. Venus has sulfuric acid clouds. Jupiter and Saturn have clouds of ammonia ice and possibly ammonium hydrosulfide at deeper levels. Titan has clouds of liquid methane. These clouds affect a planet's energy balance by reflecting sunlight and by trapping infrared radiation, contributing to greenhouse effects. They also produce precipitation. Rain falls on Earth. Titan has methane rain, and some models suggest it could rain sulfuric acid in Venus's atmosphere, though the rain evaporates before reaching the ground due to the intense heat. Greenhouse effects occur when an atmosphere allows visible sunlight to pass through but absorbs the infrared radiation that the planet's surface emits. This traps heat and warms the surface beyond what it would be without an atmosphere. Carbon dioxide and water vapor are both greenhouse gases, and their presence in Earth's atmosphere makes our planet comfortably warm rather than frozen. Venus's thick carbon dioxide atmosphere creates such an extreme greenhouse effect that surface temperatures soar to nearly 500 degrees Celsius. Understanding greenhouse effects is critical not only for understanding other planets, but also for understanding climate change on Earth as human activity increase atmospheric carbon dioxide concentrations. Magnetic fields, though not part of the atmosphere proper, interact with planetary atmospheres in important ways. Planets with strong magnetic fields like Earth and Jupiter have magnetospheres that deflect the charged particles of the solar wind, protecting their atmospheres from being stripped away. Planets without magnetic fields like Venus and Mars are more vulnerable to atmospheric loss. The solar wind can ionize atoms in the upper atmosphere and carry them away into space. Over billions of years, this process has significantly reduced Mars's atmosphere from what it once was. The study of planetary atmospheres is not just academic curiosity. By studying atmospheres on other worlds, we learn about the range of possible atmospheric states and the processes that govern them. This knowledge feeds back into our understanding of Earth's atmosphere and climate system. When we observe a runaway greenhouse effect on Venus, we gain insight into what could happen if Earth's climate were pushed beyond certain boundaries. When we see Mars's thin atmosphere and evidence of its atmospheric loss, we understand better the importance of Earth's magnetic field. When we study Jupiter's complex atmospheric dynamics, we test our fundamental understanding of fluid dynamics in rotating systems. Every planetary atmosphere is a natural laboratory, conducting experiments in physics and chemistry that we could never reproduce on Earth, teaching us lessons that extend far beyond the specific planet being studied. Mercury, the Sun's scorched companion. Mercury is a world of extremes, the smallest planet in our solar system and the closest to the Sun. It orbits at an average distance of 58 million kilometers from the solar furnace, close enough that the Sun appears 3 times larger in Mercury's sky than it does from Earth. This proximity creates an environment of almost unimaginable intensity, a realm where the laws of thermodynamics play out with relentless severity. Imagine standing on Mercury's sunlit surface at noon, though of course no human could survive such conditions. Above you, the Sun would dominate the black sky, a searing egg of fusion fire casting shadows so sharp they might cut the regolith. The day side of Mercury is scorched by solar radiation, with surface temperatures reaching 430 degrees Celsius, hot enough to melt lead, zinc, and tin. The rocks themselves radiate heat like the heating element of an oven. Yet Mercury has no atmosphere to speak of, just a tenuous exosphere of atoms knocked off of the surface by solar wind and meteorite impacts. This exosphere is so thin, 1 trillion times less dense than Earth's atmosphere, that it cannot properly be called an atmosphere at all. It is more like a collision-free environment where individual atoms follow ballistic trajectories, ejected from the surface by micrometeorite impacts or the pressure of solar photons, arcing up into space before falling back down under Mercury's weak gravity. The composition of this exosphere changes constantly, with sodium, potassium, calcium, and magnesium atoms briefly populating the space around Mercury before being swept away by the solar wind or lost to space. Without an atmosphere to distribute heat through winds and convection, each point on Mercury's surface bakes or freezes in isolation. The night side of Mercury, turned away from the Sun's fury, experiences a different kind of extreme. Here, temperatures plunge to negative 180 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. This creates a temperature difference of over 600 degrees between day and night, the most extreme temperature gradient of any planet in our solar system. No other world swings between such fierce opposites. At the terminator, the boundary between day and night, the temperature drops precipitously, falling hundreds of degrees within a few kilometers, as Mercury's slow rotation brings the dawn. Temperatures rise gradually over the course of Mercury's long day, a process that takes many Earth weeks. Mercury's surface resembles the Moon at first glance, pockmarked with craters from billions of years of impacts. A gray and ancient landscape that preserves a record of the violent early solar system when asteroids and comets were far more numerous than they are today. But closer inspection reveals differences that tell Mercury's unique story. The craters on Mercury have shallower profiles than lunar craters of similar size, a consequence of Mercury's higher surface gravity, which is about twice that of the Moon. When an impact occurs, the excavated material does not travel as far before falling back to the surface, creating a different distribution of ejecta and secondary craters. Some of Mercury's craters have bright rays of fresh material extending outward from the impact site, looking like pale streaks painted across the darker terrain. These rays consist of material excavated from beneath the surface during impacts, material that has not yet been darkened by billions of years of solar wind bombardment and micrometeorite impacts. Among Mercury's most striking features is the Caloris Basin, a massive impact crater over 1,500 kilometers across, created when an asteroid struck the planet with such immense force that it sent shock waves rippling through the entire body. The impact excavated enormous quantities of material and created a multi-ring basin with concentric scarps and ridges that mark where the crust rebounded and adjusted after the catastrophic collision. The force of the impact was so great that it generated seismic waves that traveled completely through the planet. On the opposite side of the planet, directly opposite the Caloris Basin, at the antipodal point, the shock waves focused and converged, disrupting the terrain and creating a chaotic, jumbled landscape of hills and valleys called the Weird Terrain by planetary scientists. This strange region testifies to the violence of the Caloris impact and demonstrates how a collision on one side of a planet can affect the geology on the opposite side. Between the craters, Mercury's surface shows evidence of ancient volcanic activity and tectonic features that reveal the planet's thermal history. Long cliffs called lobate scarps snake across the landscape for hundreds of kilometers, rising anywhere from a few hundred meters to over 3 kilometers above the surrounding plains. These scarps formed as the planet cooled and contracted early in its history. As Mercury's interior cooled over billions of years, the entire planet shrank slightly, decreasing in diameter by perhaps several kilometers. This global contraction caused the crust to fracture and buckle, pushing sections of crust up and over adjacent sections along thrust faults. The scarps cut across craters, indicating they formed after the major bombardment had ended. Some scarps are relatively fresh-looking with sharp features, while others are more degraded, suggesting that Mercury's contraction may have continued over an extended period, perhaps hundreds of millions of years. The smooth plains that fill some of the large impact basins suggest that Mercury once had volcanic activity, though the nature and timing of this volcanism remain topics of research. These plains are less cratered than the surrounding highlands, indicating they formed later and covered older terrain. However, unlike the Moon's dark basaltic maria that are easily visible from Earth, Mercury's plains are only subtly different in color from the surrounding terrain, suggesting a different volcanic composition or a thinner layer of volcanic material. Some of these smooth plains may have formed from impact melt rather than true volcanic eruptions, created when the immense heat of large impacts melted rock that then flowed like lava before solidifying. The volcanic and tectonic history of Mercury tells a story of a small world that was geologically active early in its history, but has been largely dormant for billions of years, its internal heat engine slowing as it cooled. Beneath Mercury's surface lies one of the planet's greatest mysteries, an enormous iron core that makes up about 80% of the planet's radius, far larger in proportion than the cores of other terrestrial planets. This gives Mercury a surprisingly high density for such a small world. Scientists are still uncertain why Mercury has such a disproportionately large core. One possibility is that Mercury formed closer to where it is now and incorporated more iron relative to rocky material because metals condense at higher temperatures than silicates. Another hypothesis suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet dominated by its core. Either way, Mercury's internal structure sets it apart from its planetary siblings. Mercury's rotation is locked into a peculiar resonance with its orbit. It rotates 3 times on its axis for every 2 orbits around the Sun, a pattern created by tidal forces from the Sun's gravity acting on Mercury's slightly elongated shape. This means that a day on Mercury, one full rotation, takes 59 Earth days, while a year takes 88 Earth days. The result is that some locations on Mercury's equator experience 2 sunrises and 2 sunsets during a single Mercurian day, as the combination of orbital and rotational motion causes the Sun to rise, set, and rise again before finally setting for the long Mercurian night. This strange dance creates one of the most unusual day-night cycles in the solar system. Despite its harsh environment, Mercury is not entirely devoid of surprises. Observations from spacecraft, particularly NASA's Messenger mission, which orbited Mercury from 2011 to 2015, revealed the presence of water ice in permanently shadowed craters at Mercury's poles. These craters are so deep and positioned such that sunlight never reaches their floors, creating pockets of permanent cold where water ice can survive despite the planet's proximity to the Sun. The ice may have been delivered by comet impacts or created by chemical reactions between hydrogen from the solar wind and oxygen in Mercury's rocks. Finding water ice on the solar system's innermost planet reminds us that even the most extreme environments can harbor unexpected pockets of stability. Mercury has a magnetic field, weak by Earth's standards but remarkable for such a small planet. Most of the magnetic fields in the solar system are generated by dynamos, currents of electrically conducting fluid moving within a planet's interior. For Earth, this fluid is molten iron in the outer core. Mercury's magnetic field suggests that it too has a partially molten core, despite being so small that it should have cooled completely billions of years ago. The persistence of liquid iron in Mercury's core might be explained by the presence of sulfur or other light elements that lower the melting point of iron, allowing the core to remain at least partially molten. This magnetic field, though weak, is strong enough to create a miniature magnetosphere that deflects some of the solar wind, providing a small measure of protection to Mercury's surface. Venus, Earth's toxic twin. Venus is often called Earth's twin because the 2 planets are remarkably similar in size and mass. Venus is only slightly smaller than Earth, with a diameter of 12,100 kilometers compared to Earth's 12,742 kilometers. Its mass is about 82% of Earth's mass. This similarity ends with the physical dimensions. In every other respect, Venus is Earth's evil twin, a world that demonstrates what happens when a planet just slightly closer to the Sun evolves down a different path. Venus is wrapped in a thick atmosphere composed of 96% carbon dioxide with clouds of sulfuric acid. The atmospheric pressure at Venus's surface is 92 times that of Earth, equivalent to being almost a kilometer beneath the ocean on Earth. This crushing pressure is enough to flatten any spacecraft that attempts to land on the surface. The thick carbon dioxide atmosphere creates a runaway greenhouse effect that makes Venus the hottest planet in the solar system despite being further from the Sun than Mercury. Surface temperatures on Venus average 470 degrees Celsius, hot enough to melt lead. And these temperatures are nearly constant across the entire planet, from equator to poles, from day side to night side. The thick atmosphere is so efficient at transporting heat that there is almost no temperature variation. The clouds of Venus are layered structures of sulfuric acid droplets that completely obscure the surface from visible light observation. These clouds reflect most of the sunlight that reaches Venus, giving the planet a brilliant appearance in Earth's sky. Venus is often the brightest object in the night sky, apart from the Moon, visible as the morning star or evening star, depending on where it is in its orbit. But beneath that bright exterior lies an environment of almost inconceivable hostility. The clouds rain sulfuric acid, though the rain evaporates long before reaching the ground because of the intense heat. Lightning flickers through the upper atmosphere, likely triggered by volcanic ash or chemical reactions in the clouds. Venus's surface, revealed by radar mapping from orbiting spacecraft, shows a complex landscape of volcanic plains, highland regions, and impact craters. The planet is geologically active, or was active in the geologically recent past. Massive volcanoes dot the landscape, some of them larger than any on Earth. Lava flows cover vast areas, testament to the planet's volcanic history. However, Venus shows no evidence of plate tectonics like Earth has. Instead, Venus appears to resurface itself periodically through massive volcanic episodes that may happen every few 100 million years, covering the entire planet with new lava flows. Evidence for this comes from the distribution of impact craters, which appear randomly distributed rather than concentrated on older terrain. This suggests that the entire surface has a similar age of around 300 to 600 million years, relatively young in geological terms. One of Venus's most peculiar characteristics is its rotation. Venus rotates backward compared to most planets in the solar system, spinning on its axis in the opposite direction to its orbit around the Sun. This retrograde rotation is extremely slow, with Venus taking 243 Earth days to complete one rotation. Combined with its orbital period of 225 Earth days, this creates a situation where a day on Venus, one full rotation, is actually longer than a Venusian year. Even more strangely, the combination of the retrograde rotation and the orbital motion means that the Sun rises in the west and sets in the east, and from sunrise to sunset takes about 117 Earth days. The reason for Venus's backward rotation remains uncertain, though most theories invoke massive impacts early in the planet's history that could have tipped it over or slowed and reversed its rotation. Venus has no magnetic field, or at most an extremely weak one. This absence is surprising, given Venus's similarity to Earth in size and mass and its presumably molten core. The lack of a magnetic field may be related to Venus's slow rotation, which might not be fast enough to generate the convective currents in the core needed to sustain a dynamo. Without a magnetic field, Venus's atmosphere is exposed directly to the solar wind, which strips away atmospheric particles over time. This process of atmospheric loss would be even more severe if not for the thickness of Venus's atmosphere, which provides some protection through sheer bulk. How did Venus become so different from Earth despite their similar origins? The answer likely lies in Venus's slightly closer orbit to the Sun. Early in Venus's history, it may have had liquid water on its surface, much like early Earth. But being closer to the Sun meant more solar heating, causing more water to evaporate. Water vapor is a greenhouse gas, so more water vapor in the atmosphere trapped more heat, causing even more water to evaporate. This runaway greenhouse effect would have eventually evaporated all of Venus's oceans. Ultraviolet light from the Sun would have broken apart water molecules in the upper atmosphere, separating hydrogen from oxygen. The light hydrogen escaped into space, while the oxygen combined with rocks on the surface. Over hundreds of millions of years, Venus lost its water and became the scorching desert world we observe today. The lesson from Venus is sobering. A planet that starts out potentially habitable can be transformed into a hellscape if conditions push the climate past certain tipping points. Earth, the blue marble. Earth is our home. The only world we know for certain harbors life, and it stands as an oasis of habitability in the harsh environment of the solar system. From space, Earth appears as a blue and white marble. Its surface dominated by liquid water oceans that cover 71% of the planet. Clouds swirl in the atmosphere, driven by solar heating and the planet's rotation. Continents appear as brown and green patches, alive with vegetation and geological activity. This view of Earth from space, first captured by astronauts during the Apollo missions, profoundly changed how humans see their planet, emphasizing its isolation, its beauty, and its fragility. What makes Earth special among planets? The answer is complex, involving many factors that interact to create conditions suitable for life. Earth orbits in the Sun's habitable zone, the range, of distances where temperatures allow liquid water to exist on a planet's surface. This zone is sometimes called the Goldilocks zone. Not too hot, not too cold, but just right. Earth's size is also important. It is large enough to retain a substantial atmosphere through gravity, but not so large that it captured a massive hydrogen-helium envelope like the giant planets did. Earth's atmosphere, composed of 78% nitrogen, 21% oxygen, and trace amounts of other gases including carbon dioxide and water vapor, is thick enough to provide warmth through the greenhouse effect and protection from space radiation, but not so thick as to create crushing surface pressure. Earth's atmosphere owes its current composition to life. The oxygen we breathe was produced by photosynthetic organisms over billions of years, transforming an early atmosphere that contained almost no free oxygen into one that is oxygen-rich. This transformation, called the Great Oxygenation Event, occurred roughly 2.4 billion years ago, when cyanobacteria evolved the ability to perform oxygenic photosynthesis, releasing oxygen as a waste product. The buildup of oxygen in the atmosphere was one of the most profound changes in Earth's history, enabling the evolution of complex multicellular life and shaping the chemistry of the planet's surface. Earth has a strong magnetic field, generated by the motion of molten iron in its outer core. This dynamo produces a magnetic field that extends tens of thousands of kilometers into space, creating the magnetosphere, a protective bubble that deflects most of the charged particles streaming from the sun in the solar wind. Without this magnetic shield, the solar wind would strip away Earth's atmosphere over geological time, much as it has done to Mars. The magnetosphere is not perfect. Some charged particles find their way to Earth's polar regions, where they interact with the upper atmosphere to create the auroras, shimmering curtains of light that dance across the night sky in high latitudes. The presence of liquid water on Earth's surface is perhaps its most defining characteristic. Water exists in all three phases: solid, liquid, and gas, and cycles between the oceans, atmosphere, and land in a complex system driven by solar energy. Water evaporates from the oceans, forms clouds, falls as rain or snow on land, flows back to the oceans through rivers, and the cycle continues. This hydrologic cycle is essential for life, distributing fresh water across the continents and weathering rocks to release nutrients. Water also has unusual properties that make it ideal for life, including a high heat capacity that moderates climate and the unusual characteristic of being less dense as a solid than as a liquid, which allows ice to float and prevents oceans from freezing solid. Earth is geologically active, with plate tectonics constantly reshaping its surface. The outer shell of the planet, the lithosphere, is broken into large plates that float on the partially molten asthenosphere beneath. These plates move at rates of a few centimeters per year, colliding to form mountains, pulling apart to create new ocean floor, and sliding past each other along fault lines. This process recycles Earth's crust, subducting old ocean floor back into the mantle where it melts and contributes to volcanic activity. Plate tectonics also plays a crucial role in Earth's climate by regulating the carbon dioxide cycle. As rocks are exposed and weathered on continents, they react with carbon dioxide from the atmosphere, eventually carrying that carbon to the oceans where it forms carbonate rocks. These rocks are subducted, and the carbon is released through volcanic activity, completing the cycle. This thermostat helps keep Earth's climate stable over hundreds of millions of years. The Moon, Earth's only natural satellite, also contributes to Earth's habitability. The Moon formed from debris created when a Mars-sized protoplanet collided with the early Earth in a massive impact about 4.5 billion years ago. The Moon stabilizes Earth's axial tilt, preventing wild variations that would cause extreme climate swings. The Moon's gravity creates tides in Earth's oceans, which may have been important for the origin of life by creating intertidal zones where early organisms could have evolved. The Moon is slowly drifting away from Earth at a rate of about 4 centimeters per year as tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit. Billions of years from now, the Moon will be much farther away, and Earth's day will be longer as the planet's rotation continues to slow. Mars, the red frontier. Mars has captivated human imagination for centuries, appearing as a reddish star in Earth's night sky and inspiring countless stories of alien civilizations. The red color comes from iron oxide, rust, in the dust that covers much of the planet's surface, giving Mars its nickname as the Red Planet. Mars is smaller than Earth, about half the diameter and 1/10 the mass, with a thin atmosphere composed mostly of carbon dioxide, at less than 1% of Earth's atmospheric pressure. Standing on the surface of Mars, you would see a butterscotch sky, tinted by the red dust suspended in the atmosphere. The sun would appear about half as large as seen from Earth, and the temperature would average negative 60 degrees Celsius, though it could rise above freezing near the equator on summer afternoons and plunge to negative 125 degrees Celsius at the winter poles. Mars is a world of stark beauty and subtle diversity. The northern hemisphere is dominated by low-lying plains covered with volcanic deposits and ancient lava flows. These northern plains are among the smoothest surfaces in the solar system, with few impact craters, suggesting they are geologically young, perhaps formed within the last few billion years. The southern hemisphere is higher in elevation and heavily cratered, preserving a record of the intense bombardment that all terrestrial planets experienced early in solar system history. This dichotomy between north and south is one of Mars's most striking features, and its origin remains debated. Some scientists suggest it resulted from a massive impact early in Mars's history, while others propose internal processes within the planet created the elevation difference. Mars hosts the largest volcano in the solar system, Olympus Mons, a massive shield volcano rising 21 kilometers above the surrounding plains. That is 2.5 times the height of Mount Everest and roughly the same as the cruising altitude of jetliners on Earth. Olympus Mons is so large that its base covers an area similar to the state of Arizona, and its gentle slopes rise so gradually that you could hike from base to summit if you had enough time and oxygen. Unlike Earth's volcanoes, which are part of mobile tectonic plates that move over stationary hotspots, Martian volcanoes remained above their magma sources for billions of years, allowing them to grow to enormous size through repeated eruptions. These volcanoes appear to be dormant now, though they may not be completely extinct. Mars also features an enormous canyon system called the Valles Marineris that stretches over 4,000 kilometers along the equator, up to 7 kilometers deep in places. This canyon dwarfs the Grand Canyon and would span the width of the United States if placed on Earth. The most tantalizing aspect of Mars is the evidence for liquid water in its past. Spacecraft orbiting Mars and rovers on its surface have found abundant evidence that water once flowed across the Martian surface. Ancient river valleys carved by flowing water snake across the highlands. Layered sedimentary rocks that could only form in the presence of water have been found in multiple locations. Minerals that require water to form, including certain clays and sulfates, have been detected across the planet. The strongest evidence comes from features that look remarkably like dried-up lake beds and river deltas, complete with rounded pebbles that could only have been shaped by flowing water. All this evidence points to a warmer, wetter Mars in its distant past, perhaps 3 to 4 billion years ago, when the planet may have had a thicker atmosphere and liquid water on its surface for extended periods. Where did the water go? Some of it remains frozen in ice caps at Mars's poles and in subsurface ice deposits detected by radar. But much of Mars's ancient atmosphere and water were lost to space. Without a strong magnetic field to protect it, the thin Martian atmosphere is directly exposed to the solar wind, which strips away atmospheric particles over time. This process, called atmospheric escape, has been directly observed by spacecraft orbiting Mars. Over billions of years, Mars lost most of its atmosphere, and as the atmospheric pressure dropped, liquid water could no longer exist on the surface. Any remaining water froze or evaporated, leaving Mars the cold, dry desert world we see today. Mars has two small moons, Phobos and Deimos, both of which are probably captured asteroids rather than moons that formed alongside Mars. Phobos orbits so close to Mars that it completes more than 3 orbits per Martian day, rising in the west and setting in the east, as seen from the surface. Tidal forces are gradually pulling Phobos closer to Mars, and in tens of millions of years it will either crash into the planet or be torn apart by tidal forces to form a ring. Deimos orbits further out and is slower, rising in the east like most solar system moons. Mars represents humanity's most likely next destination for human exploration. Multiple spacecraft from various nations have successfully reached Mars, and several rovers have explored its surface, including NASA's Curiosity and Perseverance rovers, which are currently active as of 2025. These missions have revealed Mars as a geologically diverse world with a fascinating history that may have once been habitable. The search for evidence of past or present life on Mars continues to drive exploration, making Mars not just a planet, but a frontier where we seek to answer one of humanity's oldest questions. Are we alone? Jupiter, king of planets. Jupiter dominates the outer solar system with its enormous mass and size. It is the largest planet in our solar system, with a diameter of 140,000 kilometers, more than 11 times Earth's diameter. If Jupiter were hollow, over 1,300 Earths could fit inside it. Yet, despite its size, Jupiter is not particularly dense. It is made primarily of hydrogen and helium, the same elements that make up the Sun, giving Jupiter an average density only slightly higher than water. This composition reflects Jupiter's formation in the outer solar system, where ices and gases were abundant, allowing it to grow large enough to capture a massive atmosphere from the surrounding protoplanetary disk. Jupiter radiates more heat into space than it receives from the Sun, a characteristic it shares with the other giant planets. This excess heat comes from gravitational contraction as the planet slowly shrinks, releasing gravitational potential energy. In Jupiter's deep interior, where pressures are millions of times Earth's atmospheric pressure, hydrogen is compressed into a metallic state that conducts electricity. Convection currents in this metallic hydrogen layer generate Jupiter's powerful magnetic field, the strongest of any planet in the solar system, about 20,000 times stronger than Earth's magnetic field. This magnetic field extends millions of kilometers into space, creating an enormous magnetosphere that traps charged particles in radiation belts far more intense than Earth's Van Allen belts. Any spacecraft traveling to the outer solar system must be carefully shielded to survive passage through Jupiter's radiation environment. The visible surface of Jupiter is not a solid surface but the top of its thick atmosphere, where clouds form in colorful bands that circle the planet parallel to its equator. These bands are driven by Jupiter's rapid rotation. The planet spins once every 10 hours despite its enormous size, which creates powerful winds that blow at hundreds of kilometers per hour. The light-colored bands, called zones, are regions of rising gas where ammonia ice crystals form high clouds. The darker bands, called belts, are regions of sinking gas where we can see deeper into Jupiter's atmosphere. The colors come from complex chemistry involving sulfur, phosphorus, and organic compounds that react in Jupiter's atmosphere under the influence of sunlight and lightning. Jupiter's most famous feature is the Great Red Spot, an enormous storm that has been raging for at least 300 years, and possibly much longer. The Great Red Spot is large enough to swallow Earth several times over, though observations show it has been shrinking in recent decades, and is now smaller than it was when first carefully observed in the 1800s. The storm appears as a reddish oval, and the red color likely comes from complex organic molecules created by chemical reactions driven by solar ultraviolet light. The Great Red Spot is an anticyclone, a high-pressure system that rotates counterclockwise in Jupiter's southern hemisphere. The longevity of this storm is remarkable. On Earth, hurricanes dissipate when they pass over land or colder water, but Jupiter has no land, and its energy sources are different, allowing storms to persist far longer than they could on Earth. Jupiter has at least 95 known moons, and more are discovered regularly as telescope technology improves. The 4 largest moons, discovered by Galileo Galilei in 1610, are Io, Europa, Ganymede, and Callisto, collectively called the Galilean moons. These moons are worlds in their own right, each with unique characteristics. Io is the most volcanically active body in the solar system, its surface covered with hundreds of volcanoes that erupt sulfur and sulfur dioxide, creating a colorful landscape of yellows, reds, and blacks. Io's intense volcanic activity is driven by tidal heating as Jupiter's powerful gravity squeezes and stretches the moon during its orbit. Europa has a smooth, icy surface crisscrossed with cracks and ridges, beneath which lies an ocean of liquid water. This subsurface ocean, kept liquid by tidal heating, makes Europa one of the best places in the solar system to search for life beyond Earth. Ganymede is the largest moon in the solar system, larger than the planet Mercury, and has its own magnetic field. Callisto's ancient, heavily cratered surface suggests it has remained geologically inactive for billions of years, preserving a record of the early solar system. Jupiter plays an important role in protecting the inner solar system from comet impacts. Its enormous mass and gravitational influence can deflect or capture comets and asteroids that venture into the inner solar system. Some comets are captured into orbit around Jupiter, and occasionally a comet crashes into the planet, as happened spectacularly in 1994 when comet Shoemaker Levy 9 broke apart and its fragments impacted Jupiter in a series of collisions visible from Earth. These impacts created dark scars in Jupiter's clouds that persisted for months. While Jupiter does not provide perfect protection, many comets and asteroids still reach the inner planets. Its presence likely reduces the rate of impacts, making the inner solar system somewhat safer for life. Saturn, Lord of the Rings. Saturn is perhaps the most visually stunning planet in the solar system, instantly recognizable for its magnificent ring system. Like Jupiter, Saturn is a gas giant composed primarily of hydrogen and helium, the second largest planet with a diameter 9 times that of Earth. Saturn is less dense than Jupiter, with an average density less than that of water, leading to the often repeated statement that Saturn would float if you could find an ocean large enough to hold it. This low density reflects Saturn's distance from the Sun and its smaller mass compared to Jupiter, which meant it experienced less gravitational compression and retained a fluffier structure. Saturn's atmosphere shows bands and zones similar to Jupiter's, though less vivid. Clouds of ammonia ice crystals create a pale golden appearance, and the planet experiences storms and atmospheric dynamics driven by its rapid rotation period of about 10.5 hours. One of Saturn's most remarkable atmospheric features is a persistent hexagonal jet stream at its north pole, first discovered by the Voyager spacecraft in the 1980s and studied extensively by the Cassini mission. This hexagon is enormous, with each side about 9,000 kilometers across, wider than Earth. The hexagonal shape is thought to be a manifestation of a particular pattern of atmospheric waves. But the precise mechanism that maintains such a regular shape remains a subject of research. Saturn also experiences occasional massive storms called great white spots that erupt every few decades, creating bright patches that can rival the planet's normal brightness. But Saturn's defining feature is its ring system, the most extensive and complex in the solar system. The rings extend hundreds of thousands of kilometers from the planet, yet are remarkably thin, in some places no more than 10 meters thick. If you could shrink the rings down to the thickness of a sheet of paper, they would be proportionally larger than a football field in diameter. The rings are not solid structures but are made of countless individual particles, ranging in size from dust grains to house-sized boulders, each in its own orbit around Saturn. The particles are composed primarily of water ice, which explains their high reflectivity and brilliant appearance. Some particles also contain rock and organic compounds that give certain rings a subtle tint. The origin of Saturn's rings remains uncertain. They might be remnants from a moon that was destroyed by tidal forces or an impact, or they might be leftover material from Saturn's formation that never coalesced into a moon. Evidence from the Cassini mission suggests the rings may be relatively young in astronomical terms, perhaps only a few 100 million years old, which would mean they formed long after Saturn itself. The rings are organized into multiple distinct bands separated by gaps. The most prominent gap, the Cassini division, is visible from Earth with a small telescope and is about 4,700 kilometers wide. These gaps are carved by gravitational interactions with Saturn's moons, which create orbital resonances that clear material from certain regions. Small moons, called shepherd moons, orbit within and near the rings, using their gravity to confine ring particles into narrow bands and create sharp edges. Saturn has at least 146 confirmed moons. though many of these are small irregular objects that are likely captured asteroids or fragments from collisions. The largest moon, Titan, is the only moon in the solar system with a substantial atmosphere. Titan's atmosphere is thicker than Earth's, composed primarily of nitrogen with a small amount of methane, and is so hazy that the surface is completely hidden from visible light. The atmospheric pressure at Titan's surface is 50% higher than Earth's sea level pressure. Titan's surface features lakes and seas of liquid methane and ethane, the only bodies of stable surface liquid other than Earth's water oceans known anywhere in the solar system. These hydrocarbon lakes are fed by methane rain that falls from clouds, creating a hydrological cycle similar to Earth's water cycle, but operating at temperatures of negative 179 degrees Celsius. Beneath Titan's icy crust lies another ocean, this one made of liquid water, making Titan another potential location for life in the outer solar system. Another fascinating moon is Enceladus, a small icy world that has geysers erupting from cracks near its south pole. These geysers spray water vapor and ice particles into space, some of which falls back to the surface as snow, while some escapes to form one of Saturn's outer rings. The Cassini spacecraft flew through these geysers and analyzed their composition, finding not just water, but also organic compounds and signs of hydrothermal activity beneath Enceladus's icy shell. Like Europa, Enceladus has a subsurface ocean kept liquid by tidal heating from Saturn's gravity, and the presence of organic molecules and heat sources makes it another prime target in the search for extraterrestrial life. Ice giants, Uranus and Neptune. Beyond Saturn, at the cold frontier of the planetary system, orbit the ice giants, Uranus and Neptune. These worlds mark a transition from the gas giants' hydrogen-helium dominance to planets where heavier materials like water, methane, and ammonia play a major role. Despite being called ice giants, these materials exist as hot, dense fluids in the planet's interiors, not as ice in the familiar sense. Both planets are substantially smaller than Jupiter and Saturn, but still dwarf the terrestrial planets, with Uranus about 4 times Earth's diameter and Neptune slightly smaller. Uranus is unique among planets for its extreme axial tilt. While most planets spin roughly upright relative to their orbital planes, Uranus is tipped over on its side, rotating with its axis nearly parallel to its orbital plane at an angle of 98 degrees. This means that Uranus's poles take turns pointing almost directly at the Sun as the planet orbits. Each pole experiences 42 years of continuous daylight, followed by 42 years of darkness during Uranus's 84-year orbital period. The cause of this extreme tilt is thought to be one or more massive impacts early in Uranus's history that knocked it on its side. Uranus's moons and rings orbit in the same tilted plane, suggesting the impact occurred early enough that the debris disk from which the moons formed had not yet dissipated. Uranus appears as a pale cyan disk with few visible features. Its color comes from methane in its upper atmosphere, which absorbs red light and reflects blue and green wavelengths. Unlike Jupiter and Saturn, with their vivid bands and storms, Uranus's atmosphere appears bland and featureless in visible light. though infrared observations reveal cloud structures and atmospheric dynamics that are simply not visible to the naked eye. Uranus emits very little internal heat compared to the other giant planets. Another oddity that may be related to its unusual tilt, or to something about its internal structure that prevents heat from escaping efficiently. Neptune, the outermost planet, was discovered in 1846 through mathematical predictions based on perturbations in Uranus's orbit. Neptune orbits so far from the Sun that it receives 900 times less sunlight than Earth does, yet its atmosphere is remarkably active. Neptune's deep blue color is more vivid than Uranus's pale cyan, also due to methane absorption, though some unknown atmospheric component may enhance the blue. Neptune experiences the fastest winds in the solar system, with some storm systems clocking wind speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth. The source of energy driving these ferocious winds is mysterious because Neptune, like Uranus, receives so little energy from the Sun. Neptune radiates about 2.6 times more energy than it absorbs from sunlight, suggesting internal heat sources power much of its atmospheric activity. When Voyager 2 flew past Neptune in 1989, it discovered a great dark spot similar to Jupiter's Great Red Spot, an anticyclonic storm system in Neptune's southern hemisphere. However, when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, and a new dark spot had appeared in the northern hemisphere. These observations suggest that Neptune's storms are more transient than Jupiter's, perhaps because the different atmospheric composition or internal heat flow creates different stability conditions. Neptune has 14 known moons, the largest of which is Triton, one of the strangest moons in the solar system. Triton orbits Neptune backward, in the opposite direction to Neptune's rotation, and in a tilted orbit relative to Neptune's equator. This retrograde orbit indicates that Triton was not formed alongside Neptune, but was captured from the Kuiper Belt, making it similar in composition to Pluto and other Kuiper Belt objects. Triton is geologically active despite being one of the coldest surfaces in the solar system at negative 235 degrees Celsius. Voyager 2 observed geysers erupting from Triton's surface, shooting nitrogen gas and dark material several kilometers into the thin atmosphere. The energy source for this activity may be sunlight heating a dark subsurface layer until nitrogen ice sublimates and breaks through the surface. Triton's capture put it into an elliptical orbit that has been gradually circularizing through tidal interactions with Neptune, and these tidal forces generate internal heating that may contribute to the moon's activity. Eventually, millions of years from now, tidal forces will tear Triton apart, and it will become a spectacular ring system around Neptune. Both Uranus and Neptune have ring systems, though they are much darker and less prominent than Saturn's rings. These rings were discovered through stellar occultations, observations where the planet passes in front of a star, and the rings cause additional brief dips in the star's brightness. The rings are composed of dark particles, possibly containing organic compounds processed by radiation, which makes them much harder to see than Saturn's bright, icy rings. The discovery of rings around Uranus and Neptune showed that ring systems are common features of giant planets, though their characteristics vary dramatically from one planet to another. Moons and ring systems. Worlds within worlds. The moons of our solar system are as diverse as the planets themselves, ranging from tiny, irregular rocks only a few kilometers across to world-sized satellites that dwarf some planets. More than 200 moons orbit the planets, dwarf planets, and even some asteroids in our solar system, and each one has its own story to tell. Some moons are ancient, formed alongside their parent planets from the same disk of material. Others are captured objects, asteroids or comets that wandered too close and were trapped by a planet's gravity. Still others formed from violence, created when massive impacts ejected material that coalesced into new satellites. The formation of moons follows patterns that echo planet formation, but on a smaller scale. When the giant planets formed, they were surrounded by circumplanetary disks of gas and dust, miniature versions of the protoplanetary disk around the young sun. Within these disks, material accreted into the regular satellites. Moons that orbit in the planet's equatorial plane in the same direction the planet rotates. Jupiter's Galilean moons and Saturn's major moons all formed this way, assembled from the local disk around their parent planet. These regular satellites tend to be larger and more spherical than irregular satellites because they had access to more material and formed in relatively calm environments where accretion could proceed systematically. Irregular satellites tell a different story. These moons orbit in inclined or retrograde paths, sometimes at great distances from their planet, and they often have irregular shapes suggesting they are captured objects rather than moons that formed in place. Many irregular satellites orbit in groups with similar orbital characteristics, suggesting they are fragments from a single parent body that was captured, and then shattered in a collision. The irregular satellites of the outer planets may be captured Kuiper Belt objects, icy bodies that ventured into the gravitational sphere of influence of a giant planet and were trapped. The mechanism of capture likely involved either a three-body interaction where one object was captured while another was ejected, or capture through drag in an extended atmosphere or disk of material around the young planet. Some moons are geologically active, driven by tidal heating from their parent planets. Io, Jupiter's innermost Galilean moon, is the most volcanically active body in the solar system, with hundreds of active volcanoes continuously resurfacing the moon. Io's volcanism is powered by tidal flexing, as Jupiter's gravity and the gravitational pulls of Europa and Ganymede squeeze and stretch Io during each orbit, generating enormous amounts of frictional heat in its interior. This heat melts rock and drives volcanic eruptions that spew sulfur, sulfur dioxide, and silicate lava across Io's surface. The volcanic activity is so intense that it completely resurfaces Io in only 1 million years, making it one of the youngest surfaces in the solar system. Europa presents a completely different type of activity. Beneath its icy shell lies a global ocean of liquid water, perhaps 100 kilometers deep, containing more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating, similar to that affecting Io, though less intense. Europa's surface shows a complex pattern of cracks, ridges, and disrupted terrain called chaos regions that suggests the ice shell is thin and actively deforming. In some areas, the surface looks like broken pack ice that has refrozen, suggesting that liquid or slushy material recently erupted from below. The prospect of a warm, liquid water ocean in contact with a rocky seafloor, possibly with hydrothermal vents like those on Earth's ocean floor, makes Europa one of the most promising places to search for life beyond Earth. Titan, Saturn's largest moon, is unique in having a thick atmosphere, the only moon in the solar system with an atmosphere comparable in density to a planet's. Titan's atmosphere is 98% nitrogen, with small amounts of methane and other hydrocarbons. Atmospheric pressure at Titan's surface is 1.5 times Earth's sea level pressure. The atmosphere is so thick and hazy that the surface is completely hidden from visible light observation. Titan's methane cycle mirrors Earth's water cycle, with liquid methane and ethane forming lakes and seas, evaporating into the atmosphere, condensing into clouds, and falling as rain. Titan's surface features river channels carved by flowing liquid hydrocarbons, dune fields made of organic particles, and cryovolcanoes that may erupt water-ammonia mixtures instead of silicate lava. The moon represents a kind of frozen early Earth, with complex organic chemistry occurring in the atmosphere and on the surface, though at temperatures far too cold for life as we know it. Ring systems add another layer of complexity to planetary systems. All 4 giant planets have rings, but they vary dramatically in appearance and composition. Saturn's rings are by far the most spectacular, bright and extensive, made primarily of water ice particles that range from dust-sized grains to chunks several meters across. These particles orbit Saturn in an incredibly thin disk, only tens of meters thick in some regions despite stretching hundreds of thousands of kilometers across. The origin of Saturn's rings remains debated. They might be remnants of a moon destroyed by tidal forces or an impact, or they might be primordial material that never coalesced into a moon. Recent data from the Cassini mission suggests the rings might be geologically young, perhaps only a few 100 million years old, which would make them temporary features in Saturn's history. The rings are organized into thousands of individual ringlets, separated by gaps created by gravitational resonances with Saturn's moons. The Cassini division, the most prominent gap visible from Earth, is maintained by a 2-to-1 resonance with the moon Mimas. Particles in the Cassini division orbit Saturn twice for every 1 orbit of Mimas, and Mimas's repeated gravitational tugs at the same points in those particles' orbits eventually pull them out of the gap. Small shepherd moons orbit within and beside the rings, their gravity sculpting sharp edges and keeping ring material confined to narrow bands. Prometheus and Pandora shepherd the F-ring, one of the narrower outer rings, creating a complex braided structure as their gravitational interactions stir the ring particles. Jupiter's rings are much darker and fainter than Saturn's, made of dust particles knocked off small moons by meteorite impacts. These particles spiral slowly inward due to drag from Jupiter's magnetic field and must be constantly replenished by new impacts. Uranus and Neptune also have dark ring systems, discovered through stellar occultations and later observed by Voyager 2. These rings are narrow and contain dark material, possibly organic compounds that have been processed by radiation over millions of years. The study of moons and rings reveals the full complexity of planetary systems. Planets do not exist in isolation, but are accompanied by families of smaller bodies, each influenced by and influencing the others through gravity and tidal forces. These satellite systems are laboratories for studying accretion, tidal physics, orbital dynamics, and even astrobiology. They show that interesting geological activity and potentially habitable environments can exist far from the Sun, driven by tidal energy rather than solar heating. The moons and rings remind us that when we study planets, we must consider them not as solitary objects, but as systems, collections of interacting bodies bound together by gravity and shaped by billions of years of evolution. Beyond our solar system, the exoplanet revolution. For most of human history, the only planets we knew were the ones orbiting our Sun. Philosophers speculated about other worlds around other stars, but without evidence, these remained philosophical musings. That changed in the 1990s when astronomers developed techniques sensitive enough to detect planets around distant stars. The discovery of exoplanets, planets orbiting stars other than the Sun, has revolutionized our understanding of planetary systems and revealed that the universe contains a stunning diversity of worlds that challenge our preconceptions about how planets form and what kinds of planetary systems are possible. The first confirmed exoplanet around a Sun-like star was discovered in 1995 by Swiss astronomers Michel Mayor and Didier Queloz. They detected a planet orbiting the star 51 Pegasi using the radial velocity method, which measures the tiny wobble a planet's gravity causes in its star's motion. The planet, named 51 Pegasi b, shocked the astronomical community because it was completely unlike anything in our solar system. It was a gas giant about half the mass of Jupiter, but it orbited its star every 4 days at a distance of just 7 million kilometers, 20 times closer to its star than Earth is to the Sun. This kind of planet, which came to be called a hot Jupiter, should not exist according to the theories of planet formation based on our solar system. Gas giants need to form beyond the frost line, where ice can condense to provide enough material for them to grow large, yet here was a giant planet orbiting practically on top of its star. The discovery of F1 Pegasi b opened the floodgates. Astronomers realized that hot Jupiters were relatively easy to detect with existing technology because they cause large wobbles in their stars and pass frequently in front of their stars, creating detectable dips in starlight. Over the next few years, dozens of hot Jupiters were discovered. Eventually, astronomers developed an explanation. These planets did form in the outer regions of their planetary systems as expected, but then they migrated inward through interactions with the protoplanetary disk or with other planets. This process of planetary migration can place giant planets in a wide range of final orbits, sometimes sending them spiraling inward to become hot Jupiters. As detection methods improved, astronomers began finding smaller planets. The transit method, which measures the tiny dimming of a star's light when a planet passes in front of it, became particularly powerful with the launch of NASA's Kepler Space Telescope in 2009. Kepler stared at a single patch of sky containing over 150,000 stars and monitored their brightness continuously for over 4 years. By detecting the regular dimming caused by planets transiting their stars, Kepler discovered thousands of exoplanets and revealed that planets are common throughout the galaxy. Based on Kepler's data, astronomers estimate that every star in the Milky Way has, on average, at least one planet, meaning there are hundreds of billions of planets in our galaxy alone. Kepler's discoveries revealed a new category of planet that does not exist in our solar system: super-Earths. These are planets larger than Earth but smaller than Neptune, with masses typically between 2 and 10 times Earth's mass. Super-Earths are remarkably common, perhaps the most common type of planet in the galaxy, yet we have none in our solar system. The composition of super-Earths remains uncertain. Some may be scaled-up versions of Earth, rocky planets with larger masses. Others may be mini-Neptunes, planets with rocky cores surrounded by thick hydrogen-helium atmospheres. Still others might be ocean worlds, planets where a global ocean hundreds of kilometers deep covers a rocky interior. The diversity of possible compositions makes super-Earths particularly interesting and highlights how much we still have to learn about planet types that do not exist in our solar system. Another surprising discovery was the Radius Valley, or Fulton Gap, a strange scarcity of planets with sizes between about 1.5 and 2 times Earth's diameter. Planets seem to be either smaller than this range or larger, but relatively few fall in the gap itself. This suggests something fundamental about planet formation or evolution. One explanation is that planets which grow to this critical size quickly capture hydrogen-helium atmospheres and balloon into mini-Neptunes, while planets that remain smaller lack sufficient gravity to hold onto atmospheric gas and remain rocky super-Earths. Alternatively, atmospheric loss processes might strip atmospheres from planets in this size range, pushing them down below the gap. Understanding the Radius Valley will help astronomers decode the processes that determine whether a planet becomes rocky or gassy. The discovery of exoplanets has also revealed that our solar system's architecture is not typical. Many exoplanetary systems have giant planets much closer to their stars than Jupiter's is to the Sun. Many systems have multiple planets in compact orbits, with several planets packed within the orbit of Mercury. Some systems have planets in highly elliptical orbits, rather than the nearly circular orbits of our solar system's planets. The diversity is staggering, and it suggests that many different formation and evolution pathways can produce stable planetary systems. Rather than being the template for all planetary systems, our solar system appears to be one possibility among many. Among the thousands of known exoplanets, a special focus has been on finding Earth-like planets in the habitable zones of their stars. These are rocky planets of roughly Earth's size orbiting at distances where surface temperatures could allow liquid water to exist. Several promising candidates have been found, including planets in the TRAPPIST-1 system, a star just 40 light-years away that hosts 7 Earth-sized planets, 3 of which orbit in the habitable zone. Another is Proxima Centauri b, a planet orbiting the closest star to our Sun at a distance of 4.2 light-years. Kepler 186f Kepler 452b, and dozens of others join the list of potentially habitable worlds. These planets are too far away for detailed study with current technology. We cannot see continents, oceans, or signs of life. But future telescopes will be able to analyze their atmospheres for biosignatures, chemical signs that might indicate the presence of life. The James Webb Space Telescope, launched in late 2021, represents a new era in exoplanet characterization. It can observe exoplanet atmospheres in unprecedented detail by analyzing the spectra of starlight that filters through a planet's atmosphere during a transit. Different molecules absorb light at characteristic wavelengths, creating a kind of chemical fingerprint. Webb has already detected water vapor, carbon dioxide, and methane in exoplanet atmospheres, and future observations will search for combinations of gases that might indicate biological activity, such as oxygen and methane together or other compounds that would not naturally coexist in equilibrium unless something, like life, was producing them. The exoplanet revolution has taught us that planets are ubiquitous in the universe and that they come in an astonishing variety of types. From lava worlds orbiting so close to their stars that their surfaces are molten, to frozen planets drifting in interstellar space without stars, to potentially habitable worlds that might harbor life. The diversity of exoplanets reflects the countless ways that matter can organize itself into worlds. Each new discovery expands our understanding and reminds us that the universe is far stranger and more wonderful than we imagined. The future of planetary exploration and closing. As we drift toward the end of this journey through the planetary realm, it's worth considering what remains to be discovered and what questions still whisper in the darkness, waiting for answers. Despite centuries of observation and decades of space exploration, planets still hold countless mysteries. We have barely scratched the surface of understanding how planets form and evolve, how their interiors are structured, and what processes drive their geology and atmospheres. The diversity of exoplanets challenges our theories and forces us to rethink assumptions based solely on our solar system. We do not yet know how common habitable worlds are, or whether any of them actually harbor life, quietly existing in subsurface oceans or breathable atmospheres light years away. We do not fully understand the atmospheric dynamics of giant planets or the interior structures of ice giants. We have never directly sampled the subsurface oceans of Europa or Enceladus to see what might live in those dark waters, cut off from sunlight but potentially warmed by hydrothermal vents. The coming decades will bring new missions designed to answer these questions, each one pushing the boundaries of what we can observe and measure. NASA's Europa Clipper mission will orbit Jupiter and make multiple close flybys of Europa, its suite of instruments studying the icy shell and subsurface ocean in unprecedented detail, mapping ice thickness, analyzing surface composition, and searching for plumes of water vapor erupting from the surface. The Dragonfly mission represents something entirely new, a rotorcraft that will fly through Titan's thick atmosphere, hopping from one landing site to another to explore the moon's methane lakes, organic rich surface, and complex atmospheric chemistry. This mission will search for prebiotic chemistry that might teach us about the origin of life and the conditions that existed on early Earth. Mars Sample. Return missions aim to bring Martian rocks and soil back to Earth, where they can be analyzed in laboratories with instruments far more sophisticated than those that can be sent to Mars. These samples may contain evidence of past life, preserved in ancient sediments that formed when Mars had liquid water on its surface. Even if they contain no traces of life, they will reveal details about Mars's early history and climate that cannot be obtained from orbit or from rovers. New telescopes, both in space and on the ground, will continue discovering and characterizing exoplanets, building a census of worlds that will help us understand our place in the cosmos. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across and will be able to directly image some exoplanets, studying their atmospheres and perhaps detecting signs of life. Perhaps the most profound question driving planetary exploration is whether life exists elsewhere in the universe. The sheer number of planets, hundreds of billions in our galaxy alone, and countless more in the 100 billion other galaxies we can observe, makes it statistically unlikely that Earth is unique. The chemical building blocks of life are common throughout the universe. Organic molecules have been detected in molecular clouds, in comets, on asteroids, and in the atmospheres of Titan and other bodies. The ingredients are widespread. What remains uncertain is whether the spark that animates those ingredients into living systems occurs commonly or rarely. If life is common, we might find evidence of it within our own solar system. The subsurface oceans of Europa, Enceladus, and possibly other icy moons represent environments where life could exist, protected from radiation by kilometers of ice, but with access to liquid water and possibly chemical energy from hydrothermal vents. Ancient Mars, with its rivers and lakes, might have hosted life during its warmer, wetter past, and fossils or chemical signatures of that life might be preserved in rocks. If we find life in multiple locations in our solar system, especially if that life has a separate origin from Earth life, it would suggest that life arises readily wherever conditions permit. On the other hand, if we search extensively and find nothing, it would suggest that life is rare, that Earth's story is unusual, and that we should treasure our planet's biosphere as something precious beyond measure. For life beyond the solar system, we must rely on telescopic observations. Future instruments will analyze the atmospheres of exoplanets for biosignatures, gases like oxygen, methane, and carbon dioxide in combinations that suggest biological activity. Finding oxygen and methane together in an atmosphere would be provocative, because these gases react chemically and would not coexist in equilibrium unless something was continuously producing them, as life does on Earth. Other potential biosignatures include dimethyl sulfide, produced by marine planktons, or phosphine gas that on Earth is produced by anaerobic bacteria. The search will require careful analysis because non-biological processes can also produce these gases under certain conditions. So, multiple lines of evidence will be needed before we can claim to have detected life. The study of planets connects us to the universe in an intimate way that few other sciences can match. Every atom in our bodies was forged in stars and scattered across space to eventually collect in the protoplanetary disk that formed our solar system. We are made of the same materials as planets, assembled by the same physical processes that create worlds. Carbon, nitrogen, oxygen, iron, calcium, all the elements essential for life, were once part of earlier generations of stars. When we study planets, we are studying ourselves, our origins, the deep history that made us possible. We are learning how rare or common our circumstances might be, and whether the conditions that allowed us to exist are replicated across the galaxy. Planetary science also humbles us by showing the scales of time and space involved in cosmic processes. Planets take millions of years to form and billions of years to evolve. The distances between planets in our solar system are vast, and the distances to exoplanets are incomprehensible. Light, traveling at 300,000 kilometers per second, takes hours to cross our solar system and years to reach nearby stars. When we observe an exoplanet 40 light-years away, we are seeing light that left that planet before many people reading this were born. The universe operates on timescales and distances that dwarf human experience. Yet, through science, we can comprehend these scales and understand the processes that operate across them. As you rest now, let your mind wander one last time through the images we've explored together. Picture Mercury's scorched surface glittering in the harsh sunlight. Venus's sulfuric acid clouds swirling in endless twilight. Earth's blue oceans catching the light. Mars's red deserts stretching beneath a butterscotch sky. See Jupiter's swirling bands and the great red spot. A storm larger than Earth that has raged for centuries. Watch Saturn's rings edge on, impossibly thin yet vast, made of countless particles each in its own silent orbit. Imagine the pale cyan of Uranus tipped on its side, Neptune's deep blue masked by distance and cold. Picture the hot Jupiters orbiting impossibly close to alien suns, their atmospheres boiling away into space. See the super-Earths we cannot yet truly know, the frozen worlds at the edges of the distant planetary systems, the rogue planets wandering in darkness between the stars. Each one is a world, a place with its own story stretching back to the dawn of its star system. If you found peace in this exploration, I invite you to like this video and subscribe to the channel. Your support helps this corner of quiet science reach others who seek wonder alongside rest, who find comfort in understanding the universe even as they prepare for sleep. Share your thoughts in the comments if you feel moved to do so. Tell us which planet captured your imagination, which discovery surprised you, which mystery you hope will be solved in your lifetime. For now, though, simply let go. Allow these images of distant worlds to fade into gentle thoughts. Let your breathing deepen and your body settle into rest. The planets will continue their ancient orbits through the darkness, and you can return to them anytime your mind needs to wander among worlds. The night is here, patient and quiet. The cosmos is vast beyond comprehension, filled with more worlds than we can count, more mysteries than we can solve in 1,000 lifetimes. And you, made of stardust, forged in the hearts of ancient stars and assembled on a planet that orbits an ordinary yellow star in an ordinary galaxy can rest in the knowledge that you are part of something beautiful and mysterious that stretches from the smallest grain of cosmic dust to the grandest planet circling distant suns. You are connected to it all through the very atoms of your being. Good night, fellow traveler. Sleep well beneath these same stars that shine on countless worlds.